So it says the graph of function y equals f of x is given below. So there's my f function. A table of selected values for a one-to-one function h is given. So there's that. And then g is hidden up here in the problem. So here's my g function, square root of 14x minus 3. Okay, so we're doing some compositions, just going back and practicing that. So f at 4, what is the y value on f at 4? 3. So to finish this, I'm going to evaluate h at 3, and what's the y value at 3? 5. Okay, so just using our charts, our graphs, our tables to do composition. All right, let's look at the next one. We want to start with h at 3. Okay, so h at 3 is actually what? Which one's h? The table, the graph, or the equation? The table. And so h at 3 is 5. So then I want f at 5, which comes from the graph. F at 5 is 4. Okay. All right, g of f of 7. So we're going to start on the inside and do f at 7. So we go to the graph. The y value at 7 is 2. And then for g of 2, we're going to use the equation that I was given. So that's my g function. So square root of 14 times 2 minus 3 would be the square root of 23. Did I do that right? No. Yes. No. 28 minus 3 is 25. I get there. All right. And the square root of 25 is 5. Okay. All right, so just using all of our different pieces. Okay, the next one is an inverse. Okay. What do we know happens in an inverse? We swap the x and y. Okay, we swap the x and y. So for h inverse, okay, this would be x and this would be y. Okay, so that's what we remember. In that table, the x and the y would switch. So if I want h inverse of 4, I'm going to look for 4 in the second column, all right? And then my answer is what's in the first column. So it would equal 2. All right, so you kind of have to read that one backwards. All right? All righty. Now, this one's a little bit trickier. We want to find g inverse of 9, okay? And there's a couple of ways we could go about doing that. We could take the time and actually find the inverse function for g. We could solve and do all that stuff, okay? But basically, if you think about your original g function, you got x and g of x, all right? In my inverse function, I've got g inverse, and then, no, backwards. It switches, okay? So on my g inverse function, this is x and this is y, okay? So if we think about the original, the y value from the original should be what's inside that parenthesis, okay? So let's go up here and let's take our equation. And I'm going to put 9 in for g of x. All right, because I got to find the x value that's going to match. Okay. How could I solve that equation? What would I need to do to get rid of that square root? We'd square both sides. Okay, we'd square both sides. So I get 81 equals 14x minus 3. And then we're just going to solve it out. What would I do next? Add the 3. And so 84 equals 14x. And then to get x by itself, we divide by 14. And so what would x give me? 6. That's the value of that inverse. That one's tricky. Okay. So the x value on g inverse is the y value on g. All right, so that's what I did. I took the x value in that parenthesis for g inverse, and in my g function up here, I put it where y was. So that's what we did right there. It's a cool problem, right? Very AP in nature. So testing what you know about inverses and all of that pretty quickly. Okay? All right, last one, we got this multiple composition. Remember, when we do composition, where do we start? Which function are we going to start with when I do that composition? Closest to the number. So we're going to start with h. Okay? So I'm going to go to my h, which is the table, and where x is 2, h is 4. So I keep everything else, and I put 4 in its place. Now we do it again. Okay? I go to the one nearest the number, which is f. Okay, so I'm going to keep my g. What's the y value at f when x is 4? It's 3. And then we're going to do g at 3, which is going to be my equation, 14 times 3, and then minus 3. And so if we simplify that, 14 times 3, 42, minus 3, which would give me 39. So square root of 39. So working with those multiple representations, you can count. That's going to be all over your exam in May. Okay? All over it. Questions on any of those? Okay. So today what we're going to do is we're going to work into and morph into talking about logarithmic functions. Okay, so all the things that we've done before, constructing representations, talking about key characteristics, and then rewriting things in equivalent forms. Okay, how do the properties of exponents and logarithms, how does that all kind of work together? Okay, so remember when we talked about identifying an exponential function, there were two things that we looked for. Okay, we looked for equally spaced inputs and outputs that change multiplicatively. That's a big word. In other words, we multiply by something. Okay. Now, what did we say yesterday is the relationship between exponential and logarithmic functions? How are they related? They are inverses. Okay, they undo each other. Okay, which means your x and your y's switch. It also means that they switch characteristics. So if in an exponential function we want our inputs equally spaced and our outputs changing by multiplying, guess what happens in a log function? It's the opposite, okay? Our inputs change by multiplication. And our outputs are equally spaced. All right, so let's take a look at some tables and see if we can figure out, okay, if they're exponential, are they logarithmic, are they neither one of those things? All right. So exponential, equal inputs, multiply on your outputs. Logarithms, multiply on your inputs, equally spaced on your outputs. Just switches. Okay. All right, rock and roll. Here we go. Let's look at this one together. Okay, so let's look at A. All right. Let's check our inputs. What are we doing for our inputs? I'm going up by 1. I'm adding 1 each time. Okay. What are we doing in our outputs? $16 to 8, 8 to 4, 4 to 2. Yeah, we're dividing by 2, which would be the same as multiplying by 1/2. Okay, we're dividing by 2. So the inputs are equal. We multiplied in the outputs. That's exponential. Right? Okay, so we add in 1, multiply in the other. Let's look at the next one. What are we doing on the inputs? We're multiplying by 3. What are we doing on the outputs? Yep, I'm adding 10. Okay, so when I multiply in the input and I add in the output, it's a logarithm. Okay, do those last two. Got to wear my $7 raincoat today. I was so excited. And it matched my dress. It's hanging back there on my chair. Okay, on C, what are we doing in the inputs? Yeah, we're multiplying by 10. Okay, what are we doing in the outputs? Multiplying by 2. Okay, that doesn't fit either of the things for log or exponential, so we would say neither. Okay, and then let's look at that last one. All right, what are we doing on the input? Multiplying by 2. Ooh, what about on the outputs? Subtracting 3 or adding -3. So multiply in the beginning. Oh, okay. I didn't see that one word. That made that whole text make a lot more sense. Okay. And then multiply. So this one's going to be which one? Multiply and then add. So it would be log. Okay. So question about that. Tell them the difference between the two tables. Okay. When do we have exponential? When do we have logarithmic? Okay. All right. The next thing it wants us to do is to prove that these are inverses. Remember when we talked about inverses, our compositions have to work out to be just an x. Okay, they have to work out to be just an x. And so let's do this first composition. So I want f of g of x. So I'm going to put g of x on the inside, which was log base 3 of x. And then f is 3 to that power. So 3 to the log base 3 of x. Okay, now you never seen anything like that before? It looks crazy. All right, so whatever's in that parenthesis, we put in the exponent. All right. Now, how can we show that that's really going to be x? Okay, how can we show that that's really going to be x? Well, there's a couple of ways to think about it, okay? If we did rules of logarithms, okay, and rules of exponents, if I wrote this in logarithmic form, okay, so we're saying it's equal to f of g of x, all right? The base of my logarithm is the base of the exponential function, right? So log base 3, okay, would equal y, or that f of g of x. Actually, let's just put that f of g of x right there, because that's what this is. So equal to this, f of g of x. And then it equals the exponent, which is log base 3 of x. Well, I have two logarithms that are the same, right? And so if my logs are the same, the stuff inside is the same. So what does that whole composition equal? Okay, it equals x. They're the same thing, right? Let's go the opposite direction, all right? This time we want to put f of x on the inside. So I want g of 3 to the x. Well, g is a logarithm, and it says, hey, wherever there's a variable, put what's inside that parenthesis. So I would have log base 3 of 3 to the x, okay? So that's what we're saying this composition is equal to, all right? Let's put it back in exponential form. All right, what's the base of the logarithm I know? 3. Okay, it's 3. And then we have g of f of x, right? Remember we make that big circle? So that would be g of f of x is going to equal what's inside the logarithm, which is 3 to the x. Again, if my bases are equal, then my exponents are equal. So that whole thing is equal to x. Now, here's the easy way to think about it, okay? That's why it's true, all right? But if you have an exponential function and a logarithm with that same base in your exponent, they just undo each other because they're inverses, okay? Likewise, if you have a logarithm and an exponential function in your logarithm and the bases match, they undo each other. They are inverses, okay? So you don't have to show all of this over here every time, okay? That's why it's true, right? But if we understand that they're inverses and they're going to undo each other, it leaves me with just the x that's left, okay? So I wanted you to see why it was true, but that's really all we have to do, okay? The bases match the exponent and the logarithm. You can cancel them out, and it's just what's left, all right, which is x. Okay. All righty. Let's look at the next one, okay? So still using what we know about inverses. So it says a portion of the exponential function 2 to the x is shown on the graph below. Sketch a picture of k inverse, which would be log base 2 of x. Notice they give me that line there, that y equals x line that we talked about when we did inverses. So let's pick some points that we can see, and let's flip them, okay? So a point that I can see is 0, 1. I can see 1, 2, and I can see 2, 4. All right, so those are points that I can see really well. For my inverse function, which is my logarithm, what are we going to do to those ordered pairs? Switch them. Switcheroo, 1, 0, 2, 1, and 4, 2. So let's graph those. 1, 0, 2, 1, and 4, 2. Okay. So we just switch the order pairs, okay? We're going to talk about the characteristics of the log functions here in just a second, right? But let's just investigate. We said that all exponential functions have a horizontal asymptote. So what does that mean is going to be true about your log functions? If they're inverses. They're going to have a vertical asymptote, okay? And that's exactly what we have right there, okay? You can actually see it. Here is the horizontal asymptote for the exponential function. So then here would be the vertical asymptote for the log function. Did your pen die? Okay. There's nothing worse than when your pen dies. That happened to me in the middle of a stats lesson one time. And I was like, what? Anyway. Okay. Question about that. Just picking points, switching them. All right. Ask the graph and inverse, pick some points, switch them. Okay. That doesn't change. Doesn't matter what kind of function we're dealing with. All right. And y'all know everything we do, we talk about a rate of change. Okay. So here it is again. All right. So let's look at how they're asking that question this time. Okay. It says the exponential function h of x equals a to the x contains these points, 2, 3, and 627. But they want me to find the average rate of change for the log function, log base a of x, okay, over the interval from 3 to 27, okay? So I don't really know what the log function is, but can I get the ordered pairs for the log function? Okay, let's get those. So my log ordered pairs would be what? 3, 2, and 27, 6. And so if I'm using these ordered pairs for average rate of change, what's average rate of change? It's slope. Change in y over change in x. So 6 minus 2 over 27 minus 3. And that's all we have to do with that one. Okay? So just using everything we know. Okay? Okay. Let's talk about characteristics of logarithm graphs. All right. What are those characteristics? Can we get in behaviors? Can we write the limit? So all those things that we did for exponential functions that you had a quiz on yesterday. Okay. Can we do all the same things with logarithmic functions? Right? So general form of a logarithm, f of x, is going to equal a times log base b of x. Okay? There are a couple of things that are going to have to be true. Right? Have to be true. A can't be 0. If a is 0, I don't even have a logarithm anymore. It's gone. Okay? Because I'm multiplying by a coefficient. Right? Just like in my exponential function, b can't be 1 because then it's just 1. Everything's 1 if it's 1. Okay. And finally, my base has to be greater than 0. Okay, we're not going to have a negative base. Right. My base would be bigger than 0. Okay, let's talk about domain and range. And this is where we're going to have to rely on what we know about exponential functions. Okay, what we know about exponential functions and the fact that these are inverses. Okay, so think exponential function for a second. It's growing. What was your domain on an exponential function? All real numbers, okay? It was all real numbers. So if that was domain on exponential, what's it going to be on logarithm? Range. Good. Okay. So I'm just going to sketch this so we can think about it. All right, so this is my exponential function. All right. What was my range on the exponential function? I drew it. What would my range be? 0 to infinity. So on the log, it switches, and so the domain is 0 to infinity. Okay? I can never remember that. Just remember a log function has this domain. A log function has this range. Okay? But I can remember the exponential function and switch that bad boy. Okay? And that's what I do. All right? Everything that I know about a logarithm, I base off what I know about an exponential function. Okay? Because I use exponential functions a lot more than I use a logarithm. Okay? So that's what I do there. All right? Use that exponential function as your reference. Okay? So here are pictures of two different logarithmic functions. All right? Two different ones. All right? Okay. Now, all right, so this is basically when I have a positive number in the front of the equation. The second one when I have a negative number in front of the equation. Okay? Let's talk about increasing and decreasing. If I look at the first situation, what's it doing in the graph above? Increasing, it's increasing. What about the second one? It's decreasing, all right? It doesn't do loop-de-loops somewhere along the way, right? So it's either always increasing or always decreasing. Okay, just like the exponential function. Okay, and because it's always increasing or decreasing, there are no relative extrema. Okay, you don't have any maxes and mins. Anybody lose power last night with this? Oh, I didn't, but I was just wondering. Yeah? That wind was crazy. But it did not get this. It didn't knock. I have this vase of fake flowers on my front porch. It did not knock it over. It knocked over my trash can, but it did knock that over. I was like, what? I don't know. It's what it is. I didn't even put a brick in it this year. Anyway. Okay. I'm so excited I get to put my spring decorations out over the weekend. Oh! Okay. It's just me, but did I tell you there's a bird trying to make a nest in my front porch wreath? Okay, there's no nest yet, but I think he's just coming up there and getting like little pieces of fake greenery and stuff out of it and taking it anyway. And there's also like a fake deer antlers in it for winter anyway. And so they sit on the antlers. It's so cute. Anyway. All right, let's talk concavity. All right. Looking at each example they gave me. All right. What's true about the first one? Concave up or concave down? It's down. What about the second one? It's up. So it's always concave up or concave down. It never switches. And because it never switches, there are no points of inflection. Okay. So now let's talk about end behavior. This one's going to be a little bit different, right? Because with exponentials, we had a horizontal asymptote. Looking at these logarithmic graphs, okay, we know we have to approach as x gets really, really big, as x gets really, really small, but that changes this time because what's always on one side of this graph? Yeah, the y-axis or horizontal asymptote. I could move it. I could shift it, right? But there's always a horizontal asymptote, okay? So our limit statements, we're going to always approach infinity or positive infinity, okay? We're going to approach positive infinity, and y will either increase or decrease forever, okay? So one of our limits will always be the limit as x approaches infinity, Okay, so the right side will always look like that. The limit as x approaches infinity, and my answer will either be it's getting big or it's getting small. All right, it's going up or it's going down. But our left limit, okay, x will approach the vertical asymptote from the right side, okay, because there's nothing on the left side of the asymptote, all right? It'll always, x will approach the vertical asymptote to the right, okay, from the right. And so then y will also still be positive or negative infinity, okay, because as we get close to that asymptote, I'm either going up or I'm going down, okay? So with exponential functions, we approach as x approached infinity, we approach the asymptote. That's different this time, okay? On the left side, it will always be as x approaches the vertical asymptote, okay? So I like to write it like this, right? For our left side, it'll be the limit as x approaches our vertical asymptote from the right, and I'll either get positive or negative infinity, okay? The limit will always look like that. On the right-hand side, x is going to approach positive infinity. X getting really, really big. And so my f of x, it will still be going up or down. Okay, so we're going to get infinities of some kind for both answers this time, not numbers. But one of my x values is going to approach a number. So that's different. Okay, that's different from our exponential functions. Okay, so let's do some limit statements. All right, make sure we got those. We're going to start with a couple that have pictures, and then we'll look at one that doesn't. Okay. All right, here we go. Okay. So here's my logarithmic function. The first limit that it gives me is on the left side. So it says as the limit as x approaches 0 from the right. So we're talking about going this way. Which way is my picture going? Up or down? It's going down as I get closer and closer to that asymptote, okay? So it's going down. So I would say negative infinity, right? My right-hand limit, we always start by saying the limit as x approaches positive infinity. Okay, so as x gets bigger and bigger, what's it doing on the right side? Going up or going down? It's going up, so we'd have a positive infinity. Okay. All right, let's look at the next one. Okay, so we're talking about the left side of the graph and the right side of the graph. On the left side, what's my picture getting really close to? It's getting close to my asymptote. And where's my asymptote at? It's at 0. Okay, so we're going to do the limit as x approaches 0 from the right. And it's h of x this time. And is the left side of that picture going up or going down? It's up, so it'd be positive infinity. Okay. The right side, we always stayed as the limit as x approaches infinity. Okay. Which way's the right side going? It's going down to be negative infinity. Those are always going to be opposites of each other, okay? One's going to go up and the other's going to go down, all right? So if you get one, you can get the other, all right? Now, let's look at this last one, all right? G of x equals 2 log base 3 of x, all right? Here's the only thing we need to know. Which way does this bad boy curve, okay? It's a positive number in the front, and when it's a positive in the front, it's an increasing function, okay? So when it's a positive in the front, it's an increasing function. So it's going to look something like that, all right? Did we move that logarithm anywhere on the coordinate plane? No, we left it right where it was. So my vertical asymptote is still at x equals 0, so that didn't move, okay? So my left limit's going to be the limit as x approaches 0 from the right. And my right, the limit as x approaches infinity. Okay. Which way is that left side pointing, up or down? Down. So the right side must point up. Okay. Question about that. All right, well, let's do all the things. Let's graph them, let's move them, let's transform them. Let's just do a whole bunch of stuff to them. Okay. All right. Here we go. Now, log base 3 of x, did I move it anywhere off where we start? No, okay? So that means I know I've got a vertical asymptote right here. So I'm just going to go ahead and put that bad boy in, okay? And it's going to be x equals 0. I'm writing that in, okay? So I've got my asymptote. I'm not going to cross that point. Right? Now, the question becomes, how do I graph a logarithm, all right, without a calculator? Because that's what's going to happen, okay? Here's what I tell people to do. The exponential inverse would be 3 to the x, because the base of my log is 3, okay? Do I know some ordered pairs for 3 to the x, or could I get some? Yeah, let's plug in 0. What's 3 to the 0? And what's 3 to the first? 3, okay? And that's literally enough, okay? Because my log function, the ordered pairs we actually want to graph, are inverse of that. So what are we going to do to those two ordered pairs? Switch them. 1, 0, 3, 1. Because this one didn't move anywhere, we're just going to graph them from the origin, those blue points. So from the origin, 1, 0, 1, 2, 3, and up 1, so that we kind of get an idea of what my graph's doing. Okay, and we hit a couple of points that are exact. Right? So these are our log points because we switched them. All right, so using what we know, all right. Now that we have that picture, we can answer everything else. It's all right there. Okay, what's my domain going to be for that picture? My x's that work. What about my y values? So my domain, 0 to infinity, my range, negative infinity to positive infinity. What's your x-intercept going to be? Other way around, 1, 0. Yep. Is it increasing or decreasing? It's increasing. Is it concave up or concave down? Concave down. Okay, it would spill water out, right? For in behavior, all right, let's write our two limits. All right, limit. This time, x is going to approach 0 from the right. You got to put that plus on there. Okay, we're only looking at the right side of f of x. And which way does it point on the left? Down. Okay, which means the right side, which is always the limit as x approaches infinity, has to be the opposite of that, so positive infinity. Just getting all of our info. Okay. What interesting happens on that second one? Does it stay put? No, it moves around. Okay. What would be your exponential counterpart, though? What's the base of that one? 4 to the x, okay? And that's the ordered pairs we're going to use, okay? So don't freak out about that. If we think about 4 to the x, all right, it'd be 0, 1, and 1, 4. Those are the easy points. So my switched points that we'll actually graph when we get there, 1, 0, 4, 1. Okay, so we know that's going to happen. Now, this means my asymptote's going to move, all right, because it's no longer sitting at the origin. Which way is this graph going to move? Okay, if it's inside parentheses with x, which way does it send it? Left or right, okay? Because it's plus 5, which way are we going to go? Left 5, right? And because it's minus 2 at the end, what's that going to tell me to do? Down 2, good, okay? So I'm going to go left 5, 1, 2, 3, 4, 5, down 2. I'm going to put a little mark right there, okay? Because that's what I'm going to do on my graphing. And I'm going to put in my vertical asymptote. Okay? In the original equation, which part tells me where my asymptote goes? What's in the parenthesis or at the end? Okay, so we went left 5 and down 2, all right? Once I get there to that spot where I kind of made that x, I'm going to graph just those switched ordered pairs, which means from that spot, right 1, up none, right 4, and up 1. To get my picture. See if you can do all the other pieces now. Okay. The domain, the range, the x-intercept, don't worry about that. We probably can't get that one because it didn't come out real pretty. 5. Okay. What's the domain going to be? Thinking x this time. What's the domain going to be on this one? Yeah, -5 to infinity. Okay. If we look at it, reading it across, the first place we pick up is at that asymptote. Okay, so -5 to positive infinity. All right. What about my range, the y's going up and down? Yeah, everything, all real numbers, negative infinity to positive infinity. I'm going to actually show you how to find the intercept in a second, but what about the asymptote? Where's my asymptote at? -5, yeah. We moved it back 5. Notice that comes from what's in parentheses with x, okay? That will always be your asymptote. We do the opposite because it's in parentheses. Is this function increasing or decreasing? It's increasing. Is it concave up or concave down? Down. Okay. And then let's do our 2 limits. So we're going to do the limit. This time, what's x going to approach? There you go. -5 from the right. Good job. Okay. And it's going down on that side, so it'd be negative infinity. And then limit as x approaches positive infinity for the right side. It would be the opposite, so positive infinity. Good. Okay, good, good, good. All right, let's look at these last 2 tables. These are interesting problems. This is building off of us understanding what a table looks like for a log function, where we said we multiply for x, we add and subtract for y, okay, to figure out a missing value. I think you can do the first one without me, okay? I think you can do that first one without me, but let's look and see, okay? So it gives us a table. What we want to find is the value of k, which is right here. Okay, remember with a log function, we multiply for x, we add for y. See if you can figure out what k would have to be if it's following that pattern. Okay, what do we think? It's 4. Okay, so let's look and see. In x, we just got to figure out what are we multiplying by. We got to use the values we know. Okay, 8 to 16, I'm multiplying by 2. All right, so that must be the pattern because it happens in both spots. So to get k, 2 times 2 would give me 4. Okay. And just to be sure that we have logarithm, we're adding 1 on the other side, so that's good. Okay. All right, let's look at the next one. This one a little bit harder because they wanted to be weird. Okay. What are we adding by on the right side? 7. So we're adding 7. We've got to figure out what are we multiplying by to get this next e value. And this one you got to think about a little bit. What would I multiply e to the 7th by to end up getting e to the 10th? E to the 3rd, because we would add those exponents, okay? So this is e to the 1st. If I multiplied by e to the 3rd, what would I get? I would get e to the 4th for k, all right? So using some exponent properties right there. Good stuff, okay? Good stuff. That's just using your knowledge of what a logarithmic table looks like, okay? All right, last thing we need to do, properties of logarithms. Okay, properties of logarithms. All right, Madison, y'all may not have done these, I can't remember. If in Algebra 2, because if it's not on the EOC, I don't know what Miss Mac does. You don't remember either. Okay, you couldn't tell me. All right, I do know Miss Anderson did these with y'all, the rest of y'all. She may not have done them with you, JJ. I'm not sure, buddy. But we'll look and see. They're not hard. Okay? All right, here we go. Just like with exponents, because logarithms are exponents, and there are properties of exponents, there are properties of logarithms. Okay? And so let's just kind of walk through them. The first one's called the product property. If I have a logarithm with a base of b, and I have 2 things that are being multiplied, okay? The property says I can separate that into two logarithms that are being added. So log base b of x plus log base b of y, okay? That's the property, okay? So if I have a single logarithm and things are being multiplied, I can separate those two things by adding, but they both need a logarithm, all right? So let me give you an example. If I have log base 2 of 5x, I could write that as log base 2 of 5 plus log base 2 of x, okay? That comes from that exponential property that says if the bases match, we add the exponents. That's where it comes from, okay? Because logarithms are exponents, okay? Got one base, things are being multiplied, we can separate it with addition, right? Likewise, the quotient property. If I have a log, single log, and I've got two things that are being divided, right? What do we do with exponents if they have one base and they're being divided? They have the same base that are being divided. What do we do with the exponents? We subtract. So this property says we're going to subtract. Log base b of x minus log base b of y. We subtract. Okay, so if I had log base 2 of x divided by 4, I could write that as log base 2 of x minus log base 2 of 4. All right, and then our final property is what we call a power property. So if I have log base b of x to some power, okay, so if I have a exponential expression inside my logarithm, I can pull that exponent out in front as a coefficient. Okay, so the exponent just comes out in the front. Keep the base. So that if I had log base 7 of 3 to the x would come out in front, log base 7 of 3, right? So any exponents just come out in the front. Okay. So let's talk about taking these and like putting them all together, okay? Can we take all these properties, things that have been expanded, and put them back into just one logarithm, all right? Because we're going to have to do that to solve log equations. We're going to have to take things where we have multiple logs and put them all back together, all right? So let's look at the first couple together, and then I'll let you try a few, okay? So let's look at that first one. Log base 4 of x plus log base 4 of y. The bases have to match. If they don't, we can't put them together, okay? So do my bases match? Yep, so I'm going to have a single log base 4. Because I added in the middle, we are going to multiply what was in both of those logarithms. Okay. Let's look at the second one. Do the logs match in terms of the base? Yep, so we're going to be able to use a single logarithm. I have subtraction, so inside the log, what operation would I use? Division. 5 divided by 7, or z, whatever that is. I can't even read it. Okay. All right, let's look at the next one. Do they all have the same logarithm? Yep. So I'm going to be able to use a single one, log base 10. Now, this one's interesting because I've got x minus 5 and then minus z. All right, so we're just doing a bunch of division, okay? The x has to be on top, all right? Then it's like I have 5 and then divided by z again. But what's just going to happen? Wouldn't they all end up in the same place? Okay, both of those, because they're being divided, would just end up in the denominator. Big words, denominator. Okay, so the 5 and the z would stay down there, because basically what you get is x over 5 divided by z. Okay, so I'm going to erase this in a second. Don't write it down. X over 5 divided by z. If you think fraction rules, that's x over 5 times 1 over z, so that's why it's x over 5z. Okay, that's why it's true, all right, that we can just put them both in the denominator. Okay, so just as a reminder about that. Fraction arithmetic. Okay, let's do one more. Or do y'all want to try this next one? I think you should try. All right, let's do this. You try that one. Okay. What are we going to do with this extra 3 out in front? Because I can't have a coefficient on a logarithm. Yeah, we put it back in as a power. Okay. So what I really have is log base 2 of x cubed minus log base 2 of y. Since those match, we can put them together as one logarithm, log base 2, and then what's going to be my expression inside? Yep, x cubed over y. I'd use division. All right, I'd use division. All right, here we go. Here's another one. All right. It's okay to write down multiple steps. All right, so don't panic about that. We know this 2 is going to come up as an exponent. This 5 is going to come up as an exponent. Right? So we got a lot going on there. We know we're going to divide and we're going to multiply. Okay, because I got a minus and I got a plus, and they're all a log base 7. Okay, so a log base 7. The a squared is going to stay on the top. The b to the 5th is going to go to the bottom. And then where does that 4 need to go? With the a squared. Okay, so this would be log base 7 of 4a squared over b to the 5th. Okay. Now this last one I like a lot, okay? Because when I first look at it, I'm like, well, there ain't nothing I can do to that. Done. Okay? Done. Right? But what we have to think is there a way, I mean, I could put some stuff together because there's addition here if this was written as a log base 6. Okay? So let's think for just a second. Log base 6. In order to get a 2, that means 6 to the second power is what my logarithm should have in it. What's 6 to the second power? 36. Okay, so do you see what I did there? I went backwards. I knew my final answer had to be 2. Okay, so my bases had to match for me to be able to put them together. So 6 to that answer is what should go inside that logarithm. Now I can combine them. Okay, because it's addition, I can now combine them as log base 6 of 36x. Just multiplying. All right, that one's tricky. All right, so if you have a constant, all right, inside of that, and you need to write it as one logarithm, all right, write the constant as a log with the same base. Okay, if that happens, be sure you do that. That's the only way you're going to be able to put it together with anything, because it's got to be a log base that matches. Okay? All right, just a couple more things and we're going to be done. Y'all good? You remember doing those? Okay, do you remember taking the ones that are already connected together in one and spreading them back out? I think you've got a couple of those to do. So if I went the opposite direction, so let's say I had, I'm just going to add this in. You can write it in if you want to. Let's say I had log base 5 of x squared over 3, okay? And we wanted to write it as multiple logarithms, like we wanted to spread it back out, okay? Because I have division, what's the main operation I would use between my two logarithms? Subtraction. So I'd have log base 5 of x squared minus log base 5 of 3. And we'd like to think we were done, all right? But can I leave that exponent inside? No, I'd pull it back out in front to log base 5 of x minus log base 5 of 3. So that's going backwards. They can't ask you to do that, okay? Take it to 1 or make it multiples, okay? So they could ask you to go either way. All right, so just as a reminder there. All right, let's look at this next problem because I think it's interesting what they're asking us to do, and the words are kind of weird, so let's just kind of walk through the mathematics. I think we got it. Okay, it's just using your properties. Okay, so it says the function f of x is equal to log of 6x is a horizontal dilation of the function g of x equals log x. Okay. Show that f of x can also be written as a vertical translation of g with this expression. F of x is going to equal g of x plus k. All right, there's a whole lot of words there. The only thing I can think of looking at f is that there's a 6 times x in there. I could split it apart. All right, so that's where I'm going to start. And let's see if I can make it look something like this. Oh, I didn't mean to do that. Something like this box right here, this red box. Okay. All right, so let's start with, we know f of x is log of 6x, right? If I split it apart, what would it look like? Plus log x, okay? It'd be log 6 plus log x. Now, I got to somehow get a g of x in here. All right, what do we know g of x is from what they told me? It's log x. So I'm going to take that log x out and I'm going to put a g of x there. So I have log 6 plus g of x. Well, I'm close to what they want. Okay, they want the g of x first, then they want this number. So all I got to do is switch these two. So g of x plus log 6. Okay, we've taken that. Log 6 is a number, okay? I don't know what it is, but it's a number, all right? 10 to some power, that gives me 6. And I've taken that g of x function, and I've just moved it up. It's a vertical translation, all right? I moved it up, okay? So if you ever end up with a coefficient inside the logarithm, it's actually can be written as a vertical dilation, which is kind of cool. I mean, a vertical translation. Anyway, you don't have to know that. It's just something cool that happens because of the properties. All right, change of base property. Y'all, this is something that we used to have to use all the time, all right? And the reason we had to use it all the time was because we did not have a calculator that could do logarithms, all right? I had in the back of my Algebra 2 and Pre-Cal books and my calc books, there was tables and tables and tables and tables of logarithms and what they equaled, okay? It was obnoxious, but that's what we had to do. Okay, before we had a calculator that could operate with logarithms. And what it says is this, is if I have a log of some base, okay, one of the cool things about the change of base properties is you can use any base you want. So we would have to use things like common logs because we had tables of common logs. We would have to use LNs because we had tables of LNs. So that we can get this value by taking a log with a base that I know, okay, of x, over a log of a base I know of the original base. And it would give me a really, really good approximation. Okay, it would give me a really, really good approximation, right? Now, the only reason we use that today is if I have to simplify an integral, if I have to, if they just ask me to use it, like it's just not something we use very often because we got a log button on our calculator. okay? And so we can just go for it. Only works if, obviously, your A is positive and doesn't equal 1, okay? I typically will use a common log, if they ask me to evaluate and get a numerical answer, right? But this next problem really shows us why change of base is important, okay? It gives me 2 values here, okay? It says let f of x equal log base 4 and let g of x be log base 9, all right? And we want to show that f is a vertical dilation of g by finding the value of k such that f of x equals k times g of x. Okay, there's a lot going on right there. Okay. So here's what we're going to do. We're going to start with f of x, just like we did a few minutes ago. It is log base 4 of x, all right? And looking at that, there's not a property that I could use that could expand it. There's nothing, crazy that we could do, all right? But I do know that g uses a log base 9, okay? So change of base says, you know what? I can rewrite this, all right, as log base 9 of whatever's inside, which is x, over log base 9 of whatever my base was, all right? That's what change of base says. I can use any base and divide, and it's going to give me the same value, okay? The reason I chose 9 was because that's what g of x was, right? Now, this doesn't really look like this expression that they've got right here, but I know g of x is that expression that's on the top. So I'm going to replace that expression on the top as g of x. And then I've got log base 9 of 4 right there. Okay. Well, that's just a coefficient of g of x. And if it's in the denominator, it's the same thing as 1 over log base 9 of 4 times g of x. So what that's saying in this expression they were trying to get me to do, that number is k times my g of x. Okay. Bless you. Right. That's just some algebraic manipulation. It's not pretty, but it is what it is, okay? What this is telling me is that all log functions are vertical dilations of each other. Okay, so all log functions are vertical dilations of each other. Okay. The next 2 questions, they're multiple choice, are how they're going to assess you on these properties, okay, that we just walked through. All right, those last 2 that were just kind of weird. Right. All right, here we go. Last 2, and we're calling it a day. Okay. On 11, it says, how does the graph of log base 5 of 3x compare to just plain old log base 5? Okay, how does it compare to just plain old log base 5? Let's go back a page and look at what happened when we did one like that. Okay, so go back a page. This is what we did in example 9. Okay, where we separated it with, let me get a different color, not that. Okay, where we separated it. All right, we ended up, okay, with our function and something added at the end. When I add something at an end to the function, how does it move it? If it was just plus 3, how would it move it? Up 3, okay? So if I go over here, is that a horizontal translation, a vertical translation, a vertical dilation, or a horizontal reflection? It's a vertical translation. We pushed it up, okay? This one would go up 3 because there's a 3 in there, okay? And it's weird, all All right, but that's just what it would do. We could separate it, okay? We could use the properties of logarithms. Okay, what are we doing to log base 5 of x? We're adding something to it. It's going to push it up. Okay, it's a vertical translation. Okay. Let's look at the next one. Natural log of x to the third. Let's use my properties. Okay, what are we going to do to simplify that? What can I do property-wise? Yeah, pull your 3 out in front. So I have 3 natural log of x. When I multiply in front of my function, okay, if that was 2 times x squared, what would it be? A vertical dilation. Okay, it'd be a vertical dilation. Okay, so it's a vertical dilation. All right, so we covered 3 sections today. We did a lot. Okay, we did a lot. So on your lesson practice, there's 3 different sections that we covered. So on worksheet A for 210, we're going to do 2, 3, and 6. For 211, we're going to do 2, 3, 4, 5, and 6. And then 12, 14, and 16. And then for 212, 3, 4, 6, 8, 9, 11, 12, and 13. Right? Now, tomorrow we're going to do an activity in class. Okay? Because this is the end of the 9 weeks. All right? Those of you that didn't take the quiz on yesterday need to take it, okay? Those of you that qualified for a retake, we need to do that tomorrow in class, okay, before we do the activity, all right, so that we can finalize. Will we have time? All right, JJ, you may be the only exception because you missed kind of like 3 days, okay? So we will have time, all right, for the retake for those of you that are just taking it the first time tomorrow, okay? We'll have time for that when we get back after spring break. But there's just a long time frame in there, okay? And I just, just got to be careful for those of you that were at DECA and all that good stuff, okay? All right, so activity in class tomorrow. There's your assignments. You do have a wrap-up today. Let's do it. Okay, it's on your Google Classroom. Get those points for me. Okay. Good job. All right, when we get back, we've got about 3 more sections, all right, in Unit 2.